Hello, welcome again. In the last flip lecture, we reviewed time response of first order systems. We saw how first order systems can only result in a monotonic response, which is described by exponential functions. Today, we are going to review the time response of second order systems. Second order systems description appears in many when we model many physical systems, especially for mechanical engineering. Like a typical example that we use is a mass spring damper system. You know that when we write down the governing equation of the mass spring damper system, we end up getting a second order ordinary differential equation. When we convert it into a transfer function, we end up getting a second order system which looks something like this. Similarly, not just in mechanical systems, but also in electrical systems. For example, when we have uh, uh, resistance, inductance, and capacitance all in a circuit, we end up getting uh, uh, oscillator circuits, and these are modeled using second order differential equations. Many other systems respond similar to second order systems, although their transfer function representation may be having a higher order than a second order systems. When we try to analyze these systems, uh, we often assume that their dynamics is similar to a second order system and then carry out the analysis. Therefore, the analysis of a second order system is quite important for understanding the response of many physical systems. So, in this topic, we will assume that the standard form of the transfer function is given as shown over here, where K is the system gain, zeta is referred as the damping ratio, and omega is referred as the natural frequency. Notice that in this uh, representation, in this standard form, I have the highest power of s in the denominator to be 2, but there is no uh, 0 in the numerator. So there is no term having an s in the numerator. This is not necessary. It is possible that we have a 0 or we have even two zeros inside the transfer function, and the system will still be a second order system. But for the understanding of a standard second order response, we will assume we will derive all equations and formulas based on the assumption that the transfer function takes this form. So in order to look at this response, so we can determine, so it is possible that we can take the inverse Laplace transform uh, by using a unit step response and carry out the necessary mathematics. And we can find out that in general, a second order system response is given by this formula. Actually, this is not something that that is new to you. You have looked at a response of a mass spring damper system in your McInch 222 course last year. So it is in order to understand a second order system, it is a good idea that if you do not remember uh, these these notes, if you do not remember what was taught in McInch 222, you should review this section 1.2 in your course book. So this is the course book from 2020, which is what most of you took, and in this one, you can notice that uh, we we looked at the free vibration of a mass spring damper system. There was an ordinary differential equation that was set up, and the natural response of the system was determined. So, in order to do that, you can see that this looks quite similar to this. This second equation looks quite similar to what we are using in our uh, 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 quite similar to the characteristic equation for our second order transfer function also. So characteristic equation is just the denominator equated to 0. You can see that the roots of this equation are described at locations which are related to zeta and omega n, which is something that we are going to be using in today's lecture also. And then we looked at the response of many different cases. So there was a response of the undamped case in which there is no damper. So in this case, the response is just given by a harmonic function, a purely harmonic function. And in this case, once we apply any initial conditions, the system continues to oscillate forever. Also, it shows what are the roots of the characteristic equation. So the roots are just appearing at plus minus j omega. Then for the damped free vibration, several cases were considered. The underdamped case is when zeta is less than 1. In this case, the roots of the characteristic equation are shown to be complex conjugate pairs, and these are related to zeta and omega n, and the damped natural frequency was also found in terms of omega n and zeta. The for the underdamped system, we end up getting a response which is getting attenuated over time. So the attenuation is happening exponentially. So as we go from one peak to another peak, the amplitude continues to decrease exponentially, and the rate of decay is related to the damping factor. The roots of the characteristic equation can be shown on the complex plane, where it can be seen that the distance of the roots from the origin is omega n, and the real part of the root is given by zeta omega n. The imaginary part is given by the damped natural frequency. The critically damped system is when zeta is equal to 1. In this case, we do not see any oscillations. Also, you can see that the characteristic equation, the roots end up appearing at the real pole, end up having real value only. There is no complex pole. So you can see that the lack of the complex part of the pole results in no oscillation appearing in the response. And finally, for the overdamped case, we end up getting two poles, two real poles. Again, the response is non-oscillatory, and we can see that though the critically damped system responded quite quickly by settling down to the equilibrium condition, but if we have any damping ratio value which is greater than 1, then the system will settle down at the equilibrium value at a slower rate. So among the responses which are not oscillating, which are not oscillatory, the critically damped response is going to be the fastest one. So those are just some of the quick review of what you learned in McInch 222. In case you remember this, that is okay. But if you are feeling rusty about this, about whatever I explained, please go through the course book and look at the notes on the vibration of the mass spring damper system. So today we will continue with this knowledge, and we are going to look at the response from a second order transfer function. So notice over here that while in McInch 222 you concentrated on either a free system or a case in which there were a few specific kind of forcing functions that were considered. In a transfer function approach, we assume that the transfer function is describing a relationship between the output and the input, where input can take any value. So it can, we assume, we think about, we look at the response assuming some simple input conditions like step input, the ramp input, and impulse input. But eventually, when we are analyzing the system, the analysis is valid for any arbitrary inputs that we apply to the system also. So for a step input, based on our knowledge of Laplace transforms and previous Macinch 222, we see that the response looks something like this, and we can see that for the uh, undamped system, we apply a step input, the response starts oscillating, even though the input function is a constant value. For the underdamped system, the response increases, reaches the steady state value for the first time, overshoots it by a certain value, and then oscillates around the second equilibrium condition and eventually dies down and stays close to the second equilibrium condition. Critically damped system does not have any oscillations. It reaches the second equilibrium condition in a monotonic way. If we have an overdamped system in which the damping ratio is greater than 1, then the response will continue to be non-oscillatory and reach the second equilibrium condition in a monotonic way. But among all the cases which are non-oscillatory, the critically damped system is the one which will respond the fastest. So, just similar to the Macinch 222, so if we have an undamped system where zeta is equal to 0, the transfer function will have a form which looks something like this. Here, there is the coefficient of s to the power 1 is 0. If we find out the roots of the characteristic equation, which are given by denominator s polynomial equal to 0, we end up finding two complex poles. When we look at the unit response of this is just an oscillatory response. Looking at the response from a critically damped system, we end up having a transfer function which is given by zeta equal to 1. So assuming that omega n is equal to 3, we end up getting 2 omega n as the coefficient of s. So the denominator can be factored as s plus omega n square. So we can see over here that in this case, if we take the inverse Laplace transform, the inverse Laplace transform will basically have no component which is, there is not going to be any sinusoidal or cosine term in the response. The result is that we end up going from time t is equal to 0 to infinity, we end up approaching the equilibrium condition monotonically. Notice that as t tends towards 0, both this term as well as the both the exponential term as well as the time times the exponential to the power something goes down to 0. So both the second and the third term approach 0, and all we have is the constant value. If we have overdamped system, we can expand out the, we have two poles. One of the pole now has approached closer. So notice over here that omega n is still equal to 3. So if we think about the critically damped system, both the poles were appearing at the value of omega n. But now as we increase the zeta, one of the pole has come closer to the imaginary axis, the other pole has gone further away from the imaginary axis. The inverse Laplace transform results in two exponential terms from this first order. So if we look at this, so basically we can think of it that this term can be expanded as a partial fraction of in terms of If we assume that the poles are at P1 and P2, we can expand out this transfer function uh, in terms of two partial factors, which are S plus P1 and K2 S, or it should be minus P1, S minus P1, and S minus P2. So if we think about the response of both these systems are going to respond in the exponential manner, and they result in two exponential terms which are seen in the response. Also, based on the first order response, we saw that as the pole comes closer to the imaginary axis, the response tends to be more slower. If the pole is further away from the imaginary axis, the response tends to be faster. So if we think about this overdamped system compared to the critically damped system, we can see that one of the response became closer to the imaginary axis. The other pole went further away from the imaginary axis. So compared to -3, this pole will have a faster response. Sorry, pole P1 will have a slower response and pole P2 will have a faster response. Looking at the response, overall response, we see that the response is getting dominated more and more by the pole which moves closer to the imaginary axis. So later on, as I describe to you the higher order systems, I'll describe to you that the poles which tend to be the closest to the imaginary axis dominate the overall response of the system, and they are referred as the dominant poles. So you can already see that here we have a second order system. The system responds as a combination of two poles, which is a real pole at P1 and a real pole at P2. But because it is slower, this response, because this response tends to be slower, this response is mainly dominated by the effect of the P1, and the effect of the P2 has a minor effect on the overall response of the system. Finally, for the underdamped system, we can see that we have two complex conjugate poles. And in this case, when we take when we find out the unit step response, we find that we have a sinusoidal term, which is getting multiplied by an exponential term with a negative uh, uh, negative coefficient times into time. So the effect is that as time t tends towards infinity, there is this component which is oscillating, but it is decaying over time. So the effect is that we start out from time t is equal to 0, oscillate around the second equilibrium condition, but as time t tends towards infinity, this oscillation decays down, and we end up remaining only at the constant value, which is the steady state value for this response. So based on this response, we can now look at all the specifications that I described a couple of flip lectures ago. 2 to 3 flip lectures ago, I described different transient specifications. So we defined settling time, rise time, peak time, overshoot, and uh, peak response. So based on those, we can now substitute for settling time. We can find out when the value of, for 2% settling time, we can find out when the value y becomes 0.98 of the steady state value. So 0.98 of k. We can evaluate that and we find out the 2% settling time. Rise time is the time when the response reaches the steady state from 0 to 100% for the very first time. So in that case, we can substitute y is equal to k and find out the first time instant when this at which this happens. So we can find out that the rise time is equal to this. Peak time again can be found by looking at either differentiating this response and equating it to 0 to find out the value, peak value. But it can also be noticed that this value is just half of the damped oscillation period. So for a damped oscillations, the time period will be given by 2 pi divided by omega d. Peak time is basically just the time that it takes to go from the one smallest peak to the next highest peak. So that is just half of the damped oscillation period. So this is the peak time. The maximum value can be found by substituting time t is equal to peak time, and we end up getting the maximum value, and then the percentage overshoot can be found as uh, the percentage overshoot can be found by taking this maximum value, subtracting the steady state value from it, and then expressing it as a percentage of the steady state value. So we end up getting these different specifications. Often we want to find out what is the damping, so we can also use an inverse relationship from the percentage overshoot, which only depends on the damping factor. So it's because the percentage overshoot is only depending on the damping factor, we can use uh, it to determine the damping factor corresponding to a response if we know what the percentage overshoot is. So those are the different characteristics of the time response of a second order system, and how we can relate them to the performance specifications that I want to describe. Thank you for your attention on this flip lecture. Thanks.